right, I will pass back the test. I actually didn't calculate an average.
Don't know if that's good or bad.
They'll probably have an average in lab. But like I mentioned, we're going to do corrections. I was overall pleased though. It was a decent spread of grades, but with corrections I think we'll come back up. And so with that we'll say 70% back credit. So that just means if you got like a 60 on the test and you did corrections back perfectly, to give you 40 points, you would get 70% of that. So 30 points added, so 90 total.
So is our score on the second page?
Yeah.
This looks funny. No kidding.
Yeah, we can go over stuff during
This looks funny. I know.
lab. Yeah, just ask me in lab, we can talk about it, and then we can do corrections, so that will boost everybody up. Other questions about that? All right, we're gonna see if we can get through stoichiometry today. So we're starting to talk about kind of physical and chemical changes. So physical changes are changes that only alter the state or the appearance, but not the composition. So that's going to be, of course, like water changing states, solid, liquid, gas. And so, right, this means that the atoms or molecules do not change their identity. Another example would be like something dissolving in solution. So that would be, right, they're dissolved, but they're not actually changing. You're not doing a chemical reaction. They're just going into solution. So chemical changes, of course, the fun stuff that we like in lab. Things that go boom, so things that alter the composition. And so, of course, usually we can tell there's a chemical reaction, the change in color, evolution in gas, light, heat generated, any one of those things. And so hopefully we feel comfortable. So this is where I always say, right, chemistry is cumulative just by nature. So I don't make my exams cumulative, like I won't be explicitly testing over material, but as is going to haunt us now, right, we have to know how to write our chemical formulas. So we got to keep practicing that. So we have to write our chemical formulas properly, and then we can use that to kind of figure out what our products are going to be. So we'll have our reactants. You might have to write those and then predict the product based on your reactants. And so reactions, of course, involve chemical changes, and this results in new substances. And so for us, we're just looking at a rearrangement of our atoms. And so, right, this is different from like a nuclear reaction, so that's not the same as a chemical reaction. So nuclear reaction, they're changing identities, so that's different. So different classification versus just a chemical reaction, they're just being rearranged. So nobody's changing identity. And the other key is we can balance our reaction. And so we want to do this. And this is something, like this is super important for chemistry. Like as a practicing chemist, you would do this, you know, every single day, probably multiple times a day. So like every time you set up a reaction, basically. So for a chemist, you know, an organic chemist, that could be anywhere from 1 to 10 reactions a day at least. So always important to be able to do this. And so if we look at this reaction here, So it gives us a lot of information in this short little line. So this is really how chemists communicate too. So like in their research notebook, the first thing on every page is your reaction. So what are you doing? And they write it out either like this or in all the little symbols. And so if we look at this, we're taking methane here. It also tells us the state. So we'll have, right, G for gas, L for liquid, S for solid, and then AQ means aqueous solution. And this is a lot of what we use in labs. So, you know, those little bottles are like 1 molar copper chloride or HCl. All those are aqueous solutions. So they're already in a solution for us. So they're kind of primed to react. So it's convenient for us. And so again, so methane plus oxygen, and it's telling us it's a gas, so 2 gaseous reactants, and then combine them together, and we get CO2, gas, and H2O as a liquid. And then, so also you can do some accounting, and this is what your chapter 5 homework is a lot of, is just balancing these reactions. And so you see, okay, I have 1 carbon, 4 hydrogens, and then, see, this one isn't balanced, it looks like. So we could go ahead and balance it, so I'll put a 2 there. And so notice that distributes that. And so let's see, so now my oxygens are not balanced, so I have 2 here, and then this 2 again distributes to that oxygen, telling us we have 2 equivalents, and so 4 oxygens, so we need a 2 here. So 4 oxygens, so now we can say we have a balanced reaction. So now it's balanced, so both telling us what our reactants and products are. And the reason why we want them balanced is, again, it's a rearrangement, so we're not gaining or losing atoms. So we need to have as many atoms as we started with as when we end. And so we'll do more practice before we let loose. We'll go through all the processes. So again, these chemical equations are shorthand, and it's how chemists communicate often most clearly. And so, you know, even in a paper, it may describe what's going on, but the chemist will still lay out very clearly the reaction kind of step by step, so it's really important. And so, of course, chemical equations give us the formulas. So again, your job to write the correct formula. So we said it would have the state of our reactants, and then so the relative number of reactant and product molecules, so that's all that we did up here. So that's our stoichiometry process, or balancing our equation process, just figuring out the correct numbers so we have the same on each side. And right, so this just tells us 2 relative amounts, so we'll learn how this translates. So this right now can be for 1 molecule, or 1 mole. And so everything would scale, right? So 1 molecule of methane, 2 molecules of O2, 1 molecule of CO2, 2 molecules of H2O. Or chemists usually think in moles, just because that's our physical quantity that we can hold. And so this would be 1 mole of methane, 2 moles of O2, 1 mole of CO2, and then 2 moles of water. And then, of course, later we'll translate that to quantities as well. So actual gram quantities. Because again, that's what you would do on a daily basis as a chemist, is you would need to know how much gram amount of stuff to weigh out on your little balance. That's what you do. And yes, so then we'll determine the weight, so this is coming up. And so part of how early chemists came to even discover all these elements and determine these different ratios as they kind of follow these laws. And so, of course, the big law that helped them was the law of conservation of mass. And then they balanced the equation by balancing atoms. And of course, historically, there was a lot of confusion between CO and CO2. They didn't realize that there were two different possibilities at the time, so there was a lot of combusting and confusion, but a lot of math, though, that eventually they teased out, oh, there's two different ratios of carbon and oxygen. So that's also kind of the importance of stoichiometry. You want to track your reagents, so very important. So again, that helped us identify substances early on and continues to help us in research today. And so now they've shown us the balance reactions. They balance the previous reaction we were looking at. And you can at least appreciate kind of the structures. So if this helps you, you can, write out each molecule explicitly and just see how this is translated to the physical models. If you need to borrow molecule kits, feel free so you can see, yes, I have the same number of atoms and they're just rearranging their bonds. And so that's all that happens, right? Carbon loses its 4 hydrogens and then gains oxygens, and then the other oxygens form water with those hydrogens. So everything's just rearranged. And so we have our reaction stoichiometry. And so again, the coefficients, so the 2, the 25, 16, 18, all these specify the relative amounts in moles of each of these substances. And so like we said earlier, it just scales. So we could say we're looking at 2 molecules of octane react with 25 molecules of oxygen to give us 16 molecules of carbon dioxide and 18 molecules of water. Or we'll probably be talking about our larger scale, so molar scale, so 2 moles of octane reacts with 25 moles of O2 to form 16 moles of CO2 and 18 moles of H2O. And of course, right, we can scale this by anything, so times, 1/10, and so right, and it starts to get a little redundant. So 2.5 moles. So the beauty, right, is it doesn't matter what scale you do your reaction on. This just scales up and down proportionally. So you can pick whatever scale you want to run it on. So you might say, I want to use up a gram of octane, and then you have to calculate what that is, like figure out all the relative amounts. So scale it up by 100. So everything is just a proportion. All right, and so I always say if you can cook or bake, really, so baking is the same thing, right? You have ratios of flour to sugar to oil to wet ingredients, and so it all comes together in a certain ratio. And so we can practice stoichiometry with pizza. And so we can have an ingredient for a simple pizza, so 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese. Make 1 pizza. You can just express it, of course, as a proportion. You can make conversion factors from them. And so let's say you have 10 cups of cheese, And so, right, this can be easy for some people to see, but I would still encourage you, you can set up your math. So 10 cups of cheese, then you have your ratio here. And so you always go back to your balanced equation for your ratio. So that just gives you your conversion factor. So cups of cheese goes on bottom, pizza on top. So then that cancels to give us 5 pizzas. All right, so let's, and I apologize, I didn't bring any s'mores. I kind of failed in that respect, but I know. I have to do makeup s'mores or something.
There are those little like portable campfire things.
I know.
And just heat.
Are you gonna bring one in?
I have
What's a jet burner?
We do have Bunsen burners. We can just keep
What's
gas
a
up.
jet burner, you just basically, I don't know if you those little green propane tanks and then it just attaches and then
Oh, yeah,
Oh,
those
yeah.
things.
it's basically like a portable Bunsen burner.
Oh,
but it just
yeah.
attaches to the green tanks.
Or a blowtorch. Like
Yeah.
like my grandfather has a literal like I wouldn't call it a flamethrower, but it looks pretty much like that. So I'm not sure if I can carry that around Medford all day, but I could bring it. If it's legal.
We just need some metal sticks, really.
I have those too.
Okay, bring your metal sticks. All right, Monday.
So Monday for metal sticks, all right.
Yeah, we have plenty of Bunsen burners. All right, so let's make our recipe for s'mores. So we have 2 graham crackers, of course. And we'll do 1 jumbo marshmallow. And 3 chocolates. So that equals 1 s'more. And so let's start off with some basic stoichiometry questions. So if I have 97 pieces of chocolate, and of course assuming excess of our other reagents, so how many s'mores? Give everybody.
How many s'mores you can make?
Yeah.
Or how much more, or how many ingredients you need to get?
Just how many s'mores for now? We could answer how many ingredients.
Okay. So just assuming that we have all these ingredients for 97 pieces of chocolate. Okay.
Yeah, that was the original question, but yeah, that could be step 2 of the question, right? Well, how many graham crackers do we need to pull out?
Okay.
And so I'll set it up explicitly. And again, some people will see it. Otherwise, right, just kind of set up your proportion. So you're starting with pieces of chocolate. And then always go back to your balanced equation. And so later, right, when you see chemicals, don't forget this step, because for some reason everyone forgets this. So go back and look at your coefficients. And so we have a 3-to-1 ratio. So we want s'mores on top That's what we're finding. 3 chocolates on bottom. And so what do we get for our answer?
32 and a third.
So 32 and a third, thumbs up. So 32 and a third, or you could just round it to 32, you know, if you were arguing it's whole s'mores, but.
What is even a third of a s'more? Is it a tiny little piece, like?
Yeah.
Hey, we've all been camping, we've all had that gimpy s'more where you're like kinda running out of supplies, you're like, I'll make it work.
Yeah, you gotta
My
fight.
family packs like too much, so we have like way too many leftovers, and it's a risk for the animals at that point.
You've never been camping and like the kids get into the chocolate and all of a sudden you go to make s'mores and there's like half a chocolate bar left and like 6 people and like sitting there like everybody's like sitting there breaking chocolate in half so that way you can have enough s'mores.
Why are you blaming it on the kids? For the chocolate missing?
It wasn't on the kids, I'm not gonna.
We hide it, but. I am so sorry.
Yeah, you're
Kids are
allergic
not
to.
kids, or both, you know.
You guys are funny.
Something like a butterfinger or a Reese's peanut butter cup, that's about it. After that, I'm done.
So let's look at the next type of question. And so sometimes we could have other scenarios. Yeah.
Oh, your comment about, like baking and cooking just made me think of this. So if I were to cook like an omelet, whatever, in the oven, that'd be a chemical change, right? Because the compound inside? Okay.
Yeah.
Even if it came from like a liquid to a solid? It would
Well, because you have to think about the reversibility, right? So once you cook that omelet, right, you can't do anything to it to get it back to its liquid form. And then at that point, right, you're thinking of all the enzymes that get cooked
Yeah.
and all those
like
changes.
You can't uncook a chicken breast, then, basically.
Yeah.
Okay.
So typically in these, as you said, like you could round down. For questions that are asked about this, we'll mostly specify whether or not it wants exact or whether or not it wants rounded to the closest full.
Yeah, so we'll probably do, so I do like chemistry, or I do cooking, sorry to put us in like the mindset, but we'll probably do mainly like chemistry quantities.
Yeah.
So those will be rounded like according to sig fig, so what you get. So it'll be like, you know, a student weighs something on the balance, that sort of thing.
Okay, so it'll be sig fig.
Yeah.
Okay.
Yeah. This is to try to put us in the right frame, because usually what happens with students is like, this is really easy and everyone feels good, and then for some reason we write magnesium sulfate and everyone forgets like step 1, which is just, you know, balance your equation and then refer to it. Like that's really super important. So if I have, let's see, 60 graham crackers, 45 marshmallows, and 85 chocolates. What is my limiting reagent? Or we could just ask, how many s'mores can I make? And so in chemistry, it'd be kind of asked either way. So it might ask you explicitly, like, what's the limiting reagent? Or it might give you 2 quantities and say, how much product can you make?
So
Yeah, so I might have to scroll up. You might need to look at this again. Or I'd write it somewhere. Your balanced equation, as we will call it. Or your recipe if we're cooking.
S'mores.
Yeah, or, omelets, pancakes, whatever.
It's easy to scroll back down to the problem. I haven't written out.
Oh, yeah.
I just write down like the quantity. That's such a wide variety of ingredients. I mean, like numbers, quantity wise.
You can see anything in chemistry. Because you could talk about stuff on like the industrial scale, like tons. Or you could be doing things on like the micro scale.
I don't think anyone
Milligram.
needs a ton of graham crackers, like a literal like 1 ton of graham crackers.
Maybe you were going for the Guinness World Record,
Oh God.
and make the
I feel like
largest s'more.
I feel like they're easier ones to do.
You need to do that analysis, I think, because people have been knocking them out. They just did like the world's biggest pizza again.
You ever want to make a really, really good s'more? What you do is you take Rice Krispie treats, got some flat, fry them in the frying pan, and use those as your graham crackers.
That sounds good.
Yeah, I've never heard of that.
And then you use a little bit of cinnamon. You use peanut butter cups instead of.
I think that was good.
There's also s'more croissants,
Yes.
What?
using like a buttery croissant instead of graham crackers.
Oh my gosh.
They also have this new thing, they're called, I'm trying to remember, but they actually come and they have like it's like almost looks like a small shoe stretcher. And you actually bring biscuits and you put biscuits over it and then you put it in the fire and it like cooks the biscuits. So
Oh.
they stuff it full of stuff like s'mores and stuff like that.
I think I've seen that. That would be awesome.
People are getting creative now. Amazing how easy they're making it to get fat.
Do we have,
I'm just stuck on how to convert like from like the 60 to the 45 and then to the 85 with the different kind of units, I guess. Different kind of graham crackers and unit.
so you may want to convert to something common, like the s'mores,
Oh, and then like add them together.
or compare, because you want to compare like how many s'mores can I make from 60 graham crackers? How many s'mores can I make from 45 marshmallows? And then how many s'mores from 85 chocolates? So you kind of end up doing it 3 times, which is the nature of these problems, but.
Like having repetition.
Yeah, because for a limiting reagent, you just have to test each one.
I found like one math problem online that like I had to do the quadratic formula like I swear like 10 to 15 times. It was so exhausting.
Yeah, the math teachers get really creative with their problems.
Well, it wasn't even a math teacher. It was like because they would have shown mercy. It was Blackboard.
Oh.
So of course the computer generated.
Yeah.
Or sorry, math way, but it's on Blackboard, so Blackboard supports it.
So how many s'mores do we get from 60 graham crackers? So 30, so 2 graham crackers gives us 1 s'more. And then, so for 45 marshmallows, what do we get?
45 s'mores.
So 45 s'mores. And I'll just write out the work, so that's just a 1-to-1 ratio. And what was our last number? 85 chocolates. So how many s'mores did that give us?
Full s'mores?
Yeah, how many full s'mores?
28.
So 28 s'mores. And so which one's our limiting reagent then? So chocolate,
Wait, why is that the limiting?
since that's the one, so whichever one made the least then. So basically, right, chocolate's gonna run out first, is what this is telling us.
Chocolate always runs out first.
Right?
Math to know that.
But that's, we got the math to confirm it, so limiting
Okay.
reagent. And we needed to know how many. Maybe someone's gonna make a chocolate run, I don't know.
It's not too far away from nature. I mean, it's not too far away from the stores in the app, but if you're out in the middle of nowhere, like, I'll just go to the next can found snack chocolate.
All right, so now, so this hasn't been too bad, but this has just been, so for the chemical equivalents, this is just comparing mole-mole ratios. So now we're gonna take it to what I say that is the next level. So I'll rewrite our equation here. Oops. And so we're going to change it up, though, by adding in molecular weights to this. So, right, that's what a chemist would do. So, unfortunately, we can't just count out our reagents like we could for this s'more scenario. And instead, we weigh everything in a balance. And so first, let's start off with, so 1 gram cracker is 55 grams per mole. 1 marshmallow is 78 grams per mole. And 1 chocolate is 17 grams per mole. And so let's first start off with, then what's our molecular weight then of 1 s'more?
What does it say? MW?
Molecular weight.
Oh.
And so,
What's the molecular weight for 1 s'more?
yeah. Or that could be molar mass, right? Formula weight, atomic weight. You see it abbreviated like so many ways.
Now it's grams.
Yeah, exactly. It's too easy with our crackers to crackers ratios. We got to do like chemists have to do.
Sounds like force you to weigh out every individual graham cracker.
Yeah, or just a pile of them, you know, as
Yeah,
a chemist. Although for baking, they say weight is supposed to be more accurate.
Oh yeah, definitely, if you're baking cooking, but
There's certain things that are like more important than others.
I feel like if you wanna like individually weigh like every piece of graham cracker, chocolate, marshmallow, you just have too much time on your hands. In my personal unprofessional opinion.
That's why you're weighing the pile of them, you know? You're throwing all the chocolate in the basket on the
Yeah,
scale.
you just gotta say screw it, just throw it on the scale and just, weigh it out.
Yeah, that's what we're gonna do.
When it comes to baking, you can be a little loosey-goosey with a lot of things. There's very sort of few things that you have to be super anal about.
Like sea salt to salt ratios, because I once tried to replace replace sea salt with salt for my cookies. Dear God, the, the Pacific Ocean is less saltier than the cookies I made. It was so bad. They're good cookies too. It was just so bad. The amount of salt that was in them. I was like, oh. Like, if you want to get dehydrated super quickly and increase your sodium intake by like 100%, like those are good cookies for you.
If you're gonna bake cookies and you're gonna use sea salt, use it as a topper, not mix it.
Yeah.
Oh, that's the recipe called for mixing too. So I don't have sea salt. I did normal salt. Yeah, that was a horrible mistake.
All right. Do you have an answer?
Which means I still ate them.
What do we get?
249 grams per mole.
Do we get 249? Is that what other people got? Let's do a quick check. So write 55 times 2 plus 78 plus 17 times 3. Did I make sure I didn't punch anything in? So 239. Okay, going once, going twice. So did we all at least see the method for that?
Where did that 2 come from?
The 2 graham crackers?
Oh, okay.
So yeah, we just multiplied, so 2 graham crackers. We're basically adding up, so this is kind of law of conservation of mass. We can just add up everything on our reactant side, and it should equal everything on our product side. All right, so let's try our next step. So now, if I have 300 grams of graham crackers, marshmallows, and chocolates, how many s'mores can I make? So that's 300 grams, right, of each one. So now, what's my limiting reagent?
I mean, having it all equal is a good start.
Huh?
So having it all equal is a good start.
Still got to do the same amount of math.
Are we doing full or partial?
Either one, like full s'mores or partial s'mores. It doesn't matter too much. You can give me decimal s'mores, that's fine.
We already established how much grams per mole of marshmallow, chocolate, s'mores.
Yeah, so that's right here, right? So now,
Which one was the first one? What graham cracker?
so yeah, this is 1 graham cracker is 55 grams per mole.
I could be off, but what divide the 300 by that?
So you would take 300 divided by what?
Well, like, would you add them all together and divide it by 300, or no?
I just don't know, when you say add them all together, what does that mean?
I mean, like, add the graham cracker, add the marshmallow, add the chocolate, and then you have to combine grams, and then you would take the 300 and divide it by the combined mass of all the ingredients.
So you still define though, because we know what one s'more makes, right?
Yeah.
But we can't just take, right, our 300 divided by that. It would give us, it doesn't give us, right, the accurate picture, because we need to break it down into chocolates, marshmallows, and graham crackers
Oh.
individually.
So you do it separately then?
Yeah.
Oh, okay. My math brain is trying to take over and it's causing havoc. And a lot of headaches. So what sig fix would we round to?
I probably should have given you better sig figs. We're just kind of going through the process. I'll put a decimal point there at least.
So 3 sig figs then?
Yeah.
Just want to double check.
What is that number represent if?
Which one?
If,
If I have 300 grams,
oh, if 5?
if I,
Oh, it's an I? Okay, I was like, I thought it was a number. Okay, that makes sense.
Oh, so is this just like comparing with extra steps? Because you're incorporating the moles now?
basically, yeah. So
Okay,
now,
sweet.
yeah, so the chemical translation is, right, the chemist has their pile of whatever chemical, but it's in grams. So yeah, we have to get it back to moles to do our comparison.
Okay. I'm slowly getting more to the plot.
Yeah, just keep following the plot till we see the real equations,
trying,
and
but
then
it's like,
don't forget the plot.
if you ever seen a Christopher Nolan movie, that's not Batman. It's pretty hard to keep track.
Yeah, I think our chemistry lesson is more straightforward, like Inception or something.
I don't know, there are a couple times where I'm just questioning.
So let's at least figure out, so how many s'mores can we get with 300 grams of graham cracker? So let's start with our graham cracker. And so, right, we have to convert it back to moles. So 1 mole of graham cracker. Try to write a little clearer. And so that brings us to how many individual graham crackers we have, right? So now we have moles of graham crackers, yeah.
5.45 grams per mole?
So 5.40,
5.45.
sorry, I just didn't follow you.
No, you're all good. I can't follow myself, to be honest.
So yeah, that gives us 5.45 Well, that's graham crackers, right?
Yeah, graham crackers.
And we could write that just aside here. So 5.45 graham crackers, just so we can follow. But then that's not our answer, right? So we need to know how many s'mores. So the last step, take, and I'll just put, right, conversion factor from equation. So that tells us go back to your equation. So 2 graham crackers for every 1 s'more. So 2 mole graham cracker for 1 s'more. And so now divided by 2. So now we get 2.72 s'mores with that.
Not a bad amount. Oh, well, wouldn't it be, 0.73 because it was rounding?
Oh, yeah. Sorry, I didn't pay attention. All right. So then now we have to repeat that. So we can do, right, our marshmallow next. So 300 marshmallows divided by 78. And then I'll go ahead and set up, just because it's in a 1 mole to mole ratio. And so how many s'mores can we get from our 300 grams of marshmallows? We get what we get.
Oh, wouldn't it be, so since the marshmallow is like 1 per s'more, wouldn't it be 3.85 s'mores then? Or did I jump ahead? I jumped ahead.
Oh, no, you're fine. I didn't punch it in, so I was just testing it. So, yep, so 3.85 then, so 3.85 s'mores. Getting increasingly hungry thinking about these s'mores. Of course, I'm just hungry for sugar, so that's not useful. And so let's test out our chocolate then. So our last one. So let's pick obnoxious Barbie pink. Not that I've seen the movie. And so, right, repeat the process. So it just so happens to be the same number, but, right, expect any number. So 300 grams of chocolate. And now we plug in our moles, so convert to moles. And now they're in, so right, always go back to your balanced equation, so 3-to-1 ratio. So for every 3 moles of chocolate, we make 1 s'more, so everything cancels, so we get s'mores on top. So do you have the final answer, or anybody?
For the chocolate?
Yeah,
Like the s'mores.
yeah, the s'mores.
5.87 s'mores.
So that looks good. I have 5.88, but
Oh, on my calculator, I got 17.6 divided by 3, and that equals 5.866666. Goes on until it ends at 7.
it's funny. So oops.
Oh, for the 300 divided by 17, I got 17.6. So I could have rounded. Which
Yeah.
caused difference in
So
whatever
some
happened.
some rounding discrepancy, so that's fine.
Yeah.
And so we can still tell those. So what's our limiting reagent?
Sorry, our what now?
Our limiting reagent? Yep, so our graham crackers. So now we can confidently say they were our limiting reagent, right? They made the least amount, so they're going to run out first.
They didn't hold their weight.
Yeah, or we're going to start breaking up the graham crackers, making half s'mores.
Yeah, just skip that. Just use the chocolate graham crackers, or just eat it straight off the stick. burning hot everything.
If you ever run into that, you can pour out a little bit of the marshmallows, stick a piece of chocolate in there, and roast it over the fire, and you get a gooey chocolate nut. You don't have to use the graham cracker at all.
Oh, that's smart. See, now they sell those. Have you seen like the marshmallow chocolate
The
filled?
stuffed marshmallows.
Yeah, I haven't bought them, but they're tempting. So I need to print this out for you. I'll probably give this to you during lab. And so all this is it's supposed to help you as kind of your cheat sheet as we go through all of that, so if you get kind of confused. And so I always say, right, moles is kind of our safe space. So if you can get back to moles, that's always a good place to be, right? Because once you can compare moles, that's where you can compare, right, the mole-mole ratio. And so that's really important, is that's how you compare quantities. Yes, you can technically do a gram comparison, but we're not going to go there because it's a different method, different way of thinking, and I'll confuse you if we talk about it. But some students in the past have liked that method and they just run with it. But if you don't see it, right, it's fine, don't worry about it. So mole-mole ratio, that's the best place to be. And so again, I'll print this out so you have this for your reference. But it reminds us, okay, we start with our stoichiometry. And then, so we'll look at some examples of this. We'll do some more practice for the rest of class.
There's no safe space in chemistry.
Then this is moles are your safe space. Moles is always good.
Yeah, save the moles, not us.
And so, right, let's say you're given number of particles in a problem, then you would know to either divide by Avogadro's number to get back to moles. And so that's 6.022 times 10 to the 23rd. And again, we'll do this. So this is just a conversion factor that's just defined as Avogadro's number. Again, it's related to carbon and trying to make moles equate to the periodic table, so that's how they get this funny number. And if you were going the other way, so moles, 2 particles, then you just multiply. So again, this is just a ratio. And this can be atoms, so it's usually atoms or molecules, but it's just like a baker's dozen or a dozen, or it just means things, right? So you could have a dozen atoms, so literally 12 atoms, just like you can have Avogadro's number of atoms or Avogadro's number of puppies. That'd be ridiculous. But
Puppies are amazing, like, seriously.
yeah, except all the poop, they're,
More puppies than there are people.
yeah.
Is that a bad thing, though? Like, how much, actually, no, I was saying how much damage can a puppy do, but never mind. I take it
Yeah, a
back.
lot.
I'll eat my words.
And so we'll usually do things in mass. So, right, like I mentioned, either things are powders or solids. They come in bottles. And so you'd have to use your molecular weight. And so, right, you know how to calculate that. You remember, you just add everything all up to get your molecular weight. Or, you know, as a practicing chemist, yes, they do just, you know, look at, because you have your bottle, that's going to have your molecular weight on that. So sometimes, you know, you just look up the molecular weight, like in lab or something. You don't.
What does that stoichiometry word mean again?
It's just this whole process that we've been doing. Like literally, it's a process of balancing the equation and then figuring the amount of reagent. And it could be from moles, could be from grams, or we'll practice some later with volume, right? Because you could be given a molar solution, you have 1 molar solution, 20 mils of it, how much, whatever can you make? And so that's what a chemist does on a day-to-day basis, right? And like that's what the stockroom does for us. They do all the calculations and do all the math. So we just pour the amounts, right? So we happily just like add a mil of this, yeah. But somebody has done, right, the stoichiometry before us. And so, yeah, so density, so volume, you could either be, so this could be 2 different things. So this isn't on here. So this is just density, so if you have like a liquid reagent is what this is referring to. Well, I misspelled reagent really badly. But we'll also do solution stoichiometry with a molarity. And so molarity is just moles over liters. And so you can do more stoichiometry fun. So this is like next chapter. I want to say chapter 6, which I think is next.
So we're on chapter 5. Okay, so just one now.
Yeah, but I'm just preparing you a preview because this is a lot
Oh,
of chemistry. So stoichiometry comes back to Hannes again and again is also what I'm saying. It's very important though. It's literally what chemists do. Like I literally do this like all day, every day as a practicing chemist.
I'm trying to be like a literature major, so like.
But if you want to cook, you still gotta appreciate the basics.
True. But I don't think I have to look at the periodic table when I'm cooking. At least I hope not. Because if I do, what the hell?
Yeah, but you were just talking about messing up your salt ratios. So.
True. Well, that was just me. That was human error right there.
That's cooking.
Some people like extra salty cookies. I don't know who these people are. It's sure as hell ain't me, but you know, like. Oh, okay.
All right.
Next time.
Hopefully you didn't see the answer. I was kind of scrolling around. Let's warm up with this little practice then. So how many moles of CO2 then are formed if we have 22 moles of octane combusted? And so, right, so don't freak out now just because we're seeing equations. Just you should supplement these with little graham crackers and whatever you need. So, right, it's not scary. So it shouldn't be scary just because we exchanged it. So use your same principles of a graham cracker. Should be. It should be on the page with like mole conversions.
So is that dash supposed to represent mole? Or,
Dash.
yeah, right behind the CH, oh, dash.
Oh, the L.
Oh, is that what that is now?
Yeah, this L is for liquid.
Ah, okay.
I thought it was for liters.
Yeah, so remember, right, it puts the state of matter behind it. So those are solid or
Oh.
gas. So, right, this is all gas.
Wait, what? Oh, wait. So if it's in parentheses, does that mean it's what state it's in?
Yeah.
Okay, that makes sense. Kind of. It's a little tricky, so I was like, wait a second, first it's grams, now it's gas? Like.
Yeah, when it's like that, it's listing the state. Because right now this is showing your mole-mole ratio, right? So this isn't grams or anything. So they wouldn't give you like an equation with gram ratios.
I mean, you never know, like, anything's possible in chemistry.
That's true. It's not kosher. How about that?
As long as we're doing it in this class, I'm fine. just double check, we're trying to find the moles of this.
Yeah, because it's asking for moles of CO2.
I've seen this in my book, but I do not understand it.
But we just did. It's the same thing we just did,
the
basically.
s'mores?
Yeah.
Oh, okay.
So that's the point, right? So if you can do the s'mores, so you just finished doing the s'mores, so now you could do this, right?
Overestimate my abilities.
No.
Chemistry.
Right? That's why I said just replace all these with like happy little graham crackers, right? Graham crackers and marshmallows.
So,
Because it's all just a ratio, because it's the same, that's my point, right? It's the same principle. And so what you need to be looking at, so we have our balanced chemical equation, right? This is just like our s'more recipe. It's just the numbers look funny.
would the 8 mean the moles of carbon or no? Just the because I know.
The coefficients are like this,
Oh,
like the s'more recipe. And so that's what you look at to set up your, what I call conversion factor, right? So in this case, it's asking us moles of CO2 from moles of octane. So then I would look at your, moles of CO2. So you look at your equation. So I have 16 moles of CO2. So that'd be like saying, right, I can make 16 s'mores or whatever. And I only needed 2 magical s'more machines or whatever. And so right now you just set up your conversion factor. So I'll just scroll down since this example was laid out. All right, set up your stoichiometry. So we began with 22 moles. Then, right, you set up your ratio, just like we set up our ratio of however many graham crackers to s'mores or whatever. And, right, I just pulled the coefficients from the balanced equation. And you make sure your units cancel, right? So moles of octane cancels. So you are left with moles of CO2. And I'll just plug it into the calculator. Oops. Oh. So we can all see, right? So 2 times 16 divided by, oh, that's not what, divided by 2. So we get 176. So, questions
So
so far?
22 would replace the 2, right? In front of the equation?
Yeah, well, it's like a ratio, right? So you could rewrite it. So some people see it differently where they like doing ratios, because this is basically a proportion. So you could set it up a little differently. I feel like proportions have fallen out of favor.
I can see why.
They
No offense
shouldn't.
to them, I'm just saying, like.
They shouldn't have, but, right, so then you could set up a proportion like this with x. Oops, and I wrote 2 instead of 22. So some people might see, oh, you know, you could, so 11 times 2 is 22. So some people might see it that way, so 16 times 11 would be the answer as well. You can rewrite this as a proportion differently.
I'm not sure this phrase would make sense, but I understand the numbers. I'm just confused on how we got there with the elements. Like, I'm just confused how you got C8H18 to CO2 and H2O. Like, would the oxygen element, would that apply to like the C and then the H differently?
Yeah, so right, it's what it's doing, and so right, maybe I'm not sure what part you're getting hung up on. So right, basically the oxygen is forming double bonds with CO
Okay.
and making a bunch of that. And then, right, you have 50 oxygens though. So there's 16 times 2. So 32 oxygens get wrapped up in your CO2. And then the remaining 18 serve as a platform basically for those hydrogens. And so later what we'll learn too is, so this is what's known, and this is, can't remember if this is chapter 5 or not. I need to look at the book now. Does anyone remember if they do reaction types in chapter 5? I might have to cover that. So this is a combustion reaction. And all a combustion reaction means is it's literally some hydrocarbon. And so let's do reaction types.
Types of reactions?
Yeah, is that in this chapter?
5.3.
Okay, so yeah, let's talk about this. A good lead-in. So all this is a combustion reaction, and all a combustion reaction is any carbon, hydrogen, and oxygen compound. So sometimes, right, there's no oxygen, just like in this one we were looking at. Plus oxygen gives you CO2 and water. So this is always, right, the basic formula. And so sometimes you could be given like a problem that just says you did the combustion of octane with oxygen, figure out how much CO2 and water you get, because you can balance it all out. So does that make sense? Yes, no.
I'm seeing it. I think it's a start.
Yeah, so combustion is a common one. And then, so let's,
so it's through fire that they turn into like CO2 and. Okay.
yeah. And so you can also have, so combustion, and so this starts to get into other different types. So you can also have what's called a combination reaction. And a combustion can also be a type of combination reaction, but there are also other combination reactions. So one combustion combination reaction could just be like carbon, actually let's not do carbon. Let's silicon, right, plus oxygen gives us silicon oxide. And so a combination reaction, just a simple formula. So combination is A plus B combines to give you C. So like two things forming one thing. If it's a combustion combination, it has O2. But you could have just a more general one. So another, right, combination reaction would be sodium plus chlorine to give you sodium chloride. All right, so we'll go back to types of reactions. So we'll save that for the end. I just wanted to at least touch on that because you were asking, well, how do we even know? And eventually, right, we want to get there. So we always know, okay, combustion reaction, I expect CO2, water, now I got to balance it.
So the combustion acts kind of like the way it kind of acts as like, it combines the elements together basically.
Yeah, but it also,
Combines the oxygen and the
yeah,
hydrogen.
combustion though is literally defined as hydrocarbon plus oxygen always gives you CO2 and water. And sometimes you see, and this is more of an aside.
Oh, sorry, I didn't distract. But like the first element, was that the formula for combustion? The CH5.
Yeah, so this is, right, it could be like carbon, and it doesn't matter how many carbons, right? Because there's so many organic compounds that have like different combinations. So this could be like C2H3O, or, C4H7O2, like who knows, or no oxygens. And so sometimes if you hear the term incomplete, combustion, that means that you have CO and CO2, but usually, right, you wouldn't be given that in our level of chemistry because that would be really difficult to balance, and so we're not going to see that. But just if you see that somewhere else, that's what it's referring to, is carbon monoxide formation. And so that's a safety tip, right? That's why you want to have your carbon monoxide monitor on in the winter when you're burning stuff, just in case, and make sure everything's functioning properly to have complete combustion. All right, back to our stoichiometry. And so, right, we did this before, so we practiced this with our graham crackers. So the point is now we're just putting ourselves in a chemistry frame of mind. And so, right, we always want to get to our stoichiometric ratio to, balance them. And again, right, think of the ratios if this is better for some people. All right, so now let's try this problem. Yeah, and so, right, don't get scared because chemistry can deal with huge quantities, tiny quantities. So now we're doing the really large.
I've been terrified, man. I'll be honest with you. I've been terrified.
Just step by step. You can't let the big numbers intimidate you. Like, that's the
Too
point.
late.
That's the point, though. Don't let them scare you. They're just there to scare you. Like, so try this problem. So we have 3.6 times 10 to the 15 grams of octane, burn in excess oxygen. They're asking for mass of CO2. And so it kind of tells you the strategy. So maybe I'll give the hint. But just try that on your own, right? It's still the same thing like the graham cracker problem. So think back, right? You were given grams, so then you divided to get back to moles. Then you go to your mole-mole ratio still. It's all the same process.
So by saying it needs a balanced reaction, does that imply that the reaction is not balanced already, like the equation's not balanced?
Well, you should always check it. So in this case, we were given a balanced equation, but you shouldn't assume that you're given a balanced equation.
Okay, that makes sense.
Usually I try to be nice on an exam and I say like this unbalanced reaction or like step one balance it
Yeah, I
type of thing.
appreciate that.
Yeah. But, maybe on the homework it doesn't always say. Or if you read a word problem, it's not going to be balanced, right? It'll just be like, oh, iron sulfide and calcium chloride reacted or something. Go. Okay, do we have answers or? No, but you had answers in the other ones.
I didn't really know where to start, still.
So all right, let's do
I
it
have a
together.
Kind of a guess.
Well, all right, walk us through. So where did you start then?
I started by taking the 3.6 times 10 to the 15th grams, and then I did multiplied it by the ratio of how many CH18s to this CO2s. So I got 3.6 times 10 to the 15th times
Wait, I think we skipped a step though. Yeah, so we didn't go to moles. See, so as soon as we looked at chemicals, we freaked out.
Yeah.
So what didn't I give you?
So it should be 6.022 times 10 to the 23rd.
No, we don't need that one.
That's where I'm confused.
So what did I give you here?
Grams per mole.
So grams per mole, right? So we need the molecular weight of CO2. And then how do we get that? We learned that. Yeah, the periodic table.
What?
Oh, that's what I missed. Okay.
Yeah.
That's what I missed.
So we add everything up. So looking at the periodic table, right, carbon is 12 plus 2 times 16 or 15.99, whatever. So what's our mass of CO2 then? Roughly.
44.
Yeah, so 44, and that's a good estimate. So 44 grams per mole. So I just didn't give you that information, right? With the graham cracker s'more problem, we were given that really explicitly. But with chemistry, right, you can always find it. So you can always add it up.
Do
No.
we need to find the grams per mole for the CH18?
Yeah, so we need to do that as well. So we'll need this. And so let's get our molecular weight of this as well. So what's CH18?
12 times 8, and then 1 times 114.
So 114 grams per mole. So now we have what we need. So yeah, now we start, so they gave us the strategy, right? But we want to just do it for ourselves. So the first thing you might want to do when you see a problem, right, we need mass of CO2, so we needed molecular weight of CO2, and then we needed molecular weight of octane to begin. So then we set that up. So octane. So now we go grams. So we want to go from grams to moles, right? So now we plug in our molecular weight of octane. So 114 grams for every 1 mole of octane. And so we wanted to just set this up in one big math thing. So
Wait,
then,
3.6 and that's all one?
what, 3.6 times 10 to the
Over here.
15?
That's all of that is over one?
Yeah. Right, because this is 3.6 times 10 to the 15 grams of octane. So this is just saying what we started with. Then, right, this gives us moles of octane, so I'm just reminding us. And so now we can compare, right, our mole-mole ratio, just like we did before. So this would be like finding out how many s'mores we can make. How many CO2 molecules can we make? So you go back to your equation. So for every 2 equivalents of octane, you make 16 grams of CO2, right? So now we do our conversion factor. So I'll kind of draw arrow, right? Plug this in. So this is just our ratio. So for every 2 moles of octane, we said we made 16 moles of CO2. So right now we have moles of CO2 calculated from this. But then the last part was they wanted grams. And so now we can plug in our last bit. So times 44 grams per 1 mole. And so you can always calculate it right step by step if that makes you feel better. So now we just have to plug everything in. So divide it by 114 first. So that gives us moles of octane. So times 16. Yeah, we'll just do that. So times 8.
Wait, what did you just say, Dave?
Because 16 over 2 is 8.
Yeah, so just,
Oh, you combine them.
yeah, just,
Times 44. Okay, that makes sense-ish.
so about 1.11.
So, but then you would use the, wouldn't it be 1.1 for the sig figs? Because you started out with
Oh,
1.6.
yeah.
I feel like there's a lot more steps in converting graham crackers in a school.
No, but it wasn't. We just added one tiny little step of, we had to calculate the molecular weight. That's the only thing I didn't give you that was different. And then it just looked scarier because it was octane, C8H18, and not like graham cracker and marshmallow.
Where does 1 times 10 to the 16 come from?
That's your answer.
Yeah, well, there's a problem.
So this is where it came from.
I get it now.
Oh.
So let's try this one now. And so let's look at what type of reaction this is. So this one gives you the products, but let's look at what's fundamentally going on. And so this is what's called a double displacement reaction. So this is pretty common, and we'll look at some today, I think, in lab. And so they follow this pattern of like A, B, C, D, gives you new, right, B, C, A, D. So they just swap partners around. And so let's rewrite this now. So double displacement, again, AB plus CD, they just swap. And so there's kind of a key though, because now you might be asking, well, how do you know what reacts then? And so the double displacement reaction has to be driven by something. And so in this case, this is actually a special type of double displacement, so it's a neutralization, and it tells us that. So neutralization is just base plus acid, but it's still fundamentally a double displacement. It's just driven by the production of water. So that's one way to drive a double displacement. So driven by formation of water, or the other way is driven by a precipitate. And so what does that mean? So let's look at some example. So we could take silver nitrate plus sodium chloride. And so we have to think about what that would look like in solution. And we might need some solubility rules later, is what this is leading to. Yeah, so silver chloride. So those would be your two products. And so now we're getting to the right idea. So right, you're thinking what's floating around in solution. These are your potential new partners. And we'll get to this in the course, and I probably need to print out another sheet for you. But you would look at your solubility rules. And basically, I know, so sodium nitrate, so sodium is usually always soluble, nitrates are always soluble, so this is aqueous, meaning it's not going to come together and form a precipitate. But again, you'll do this in lab, at least I'm pretty sure you do it today, and you'll be observing a precipitate, and that just means some cloudiness will form, and that just means they drop out of solution because they're so insoluble. You'll actually get to see that. So that's what drives that. Again, we'll kind of keep looking at these reaction types. And they are covered in your lab today.
Is that like what happened when we did the silver test with the one that like formed those like weird colored chunks on the bottom?
Exactly, yeah. So anytime you get precipitation, chunky, cloudy, that probably means you're forming a precipitate. So yeah, that's exactly what was happening. Because the silver tends to be insoluble, so you make different compounds. But yeah, with the nitrates, right, so that's why we said, so thinking back to that lab, if you already had a nitrate, though, and you try to add silver nitrate, that's why it said there'd be no reaction. Because in solution, it's just a bunch of silver and nitrate looking at each other still, so it's nothing to drop out. And again, we'll keep talking about this. So let's go back. We'll save some time at the end still to go over the other reaction types. But let's practice our stoichiometry. So see if we can calculate this. So what mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? And so, right, don't forget to calculate your molecular weights.
And you found that like bottom periodic table of each element?
Yeah, so that's right, the average atomic mass, and then you add them all up.
So chapter 5 due this week or next week?
I think it's due on Monday of next week.
Okay, so we'll check.
Yeah, because we're supposed to get through all of chapter 5.
Are we just rounding the whole numbers, or are we almost, like, if it's like 24.3, are we doing 24.3 or just 24?
I'd probably round it to 24.3 just to follow like these sig figs here.
Okay, so try to keep it to the same amount of sig figs when you're rounding. Okay.
Yeah, but that's where there's going to be discrepancy, so just try not to truncate too much.
HCU stand for again?
So that means aqueous, so like aqueous solution. And so if it's on the product side, it's just telling you it's still gonna be in solution. Let's see, do we have answers or still? Okay, I think there's still any time. Do you have an answer or walk us through what you did?
So first off, I got the grams per moles for each one of those. So I started with the MgOH2, which came up to be 58.3 grams per mole.
58.083. Is that what other people?
I've got 58.3.
Oh, my bad. Sorry, I just didn't hear you. So 58.3 grams per mole. So is that what other people got, or something like that?
You
Yeah.
got that
I
from
got
adding up the.
58.
Yeah, 58's fine.
Would that work?
Yeah. But you probably want to give yourself more sig figs.
So,
Yeah, just at least try to match. Yeah.
The magnesium, I got the 24.3, that's why I asked. And then the oxygen got rounded itself to 16, and then the hydrogen rounded itself to 1.
Yeah. Yeah, so I like 58.3.
And then for the HCl, I got 36.5.
So 36.5. And so same thing, there could be a little discrepancy. I probably wouldn't round to 37 just because that's a lot of rounding early.
So then I took the 3.26 grams of MgOH2 over 1, and then I timed it by 1 mole over 58.3 grams,
And I think, yeah.
because 1 mole of that equals 58.3 grams.
For,
And then I did the conversion of, for every 1 MgOH on bottom, it equals 2 hydrochloric. And then I multiplied that by 36.5 grams for every 1 mole of HCl.
that looks excellent.
And it came out to be 4.08 grams rounded.
So is that what other people got? 4.08 you said?
Yeah.
Question?
Where'd the 2HCl come from?
So right, this comes from your balanced equation. So this is like your graham cracker ratio.
Oh, okay.
Yeah, so the same idea. So right, for every 1 molecule of magnesium, you need 2 HCl molecules.
Oh, so that's where you get the ratio. Okay.
Yeah.
That would just be 4.08 grams, not grams per mole.
Oh, yeah, sorry.
I just wanted to make sure.
What does that
Yeah.
bottom number say, 1 over 1?
1 mole of HCl, which one?
Yeah,
Yeah.
1 mole of HCl or 1 mole of magnesium hydroxide.
Oh, what's that above the one your cursor's at? Yeah, what's that?
2 moles of HCl, so this is right your ratio.
2 moles HCl.
So this is just expressing this part. So for every 2 moles of hydrochloric acid, we have 1 mole.
Oh, 2 moles of HCl, okay. I just want to double check. So the compound names kind of acts as like units of measurement then, or like how you usually put like you convert it to like grams, but this time we're converting it to different compounds. That makes any sense? I'm trying to understand it.
So, right, all we're doing is we're just going from like grams of something to moles to back to grams of our final product.
Oh, okay.
And I don't know if you're kind of thinking, see, this is where I think you start thinking of like mass to mass ratio conversion, which again isn't wrong, it's just can confuse you if you mix it up with stoichiometry. So that's why I say like go through the process. But where do people get stuck on this? Because I saw everyone like writing down furiously, but what tripped us up? Because we were just fine with the graham crackers and the pizza.
I think me understanding where the mass comes into play is helping a lot though too. Because originally I was confused on how we got some of the numbers, but now I know that some of it's the mass, and we're just converting mass into moles. I think it's helping a lot.
Yeah. So is
I'd say the ratio definitely makes me up because the previous problem was given, but on this one you have to find it yourself.
yeah, and that's where I say, right, don't forget what your chemical equation is trying to tell you. So, right, always refer back to it. So, right, don't forget that step. So, always look back. So, always refer back, right? That's where you get your mole ratio. And, you know, maybe you want to write that out first, too. So, you kind of have to establish, too, like what steps you need. So maybe you see, okay, if we're doing HCl and milk of magnesia, maybe the first step you want to do is look at your equation and go, well, I already know for every one equivalent of magnesium hydroxide, right, I need 2 equivalents of HCl. So maybe you need to put that aside already as your conversion factor. And just like we learned in the beginning, right, it doesn't matter which one we put on top, HCl or magnesium, it's just a conversion factor. So it's just which one needs to be on top, which one needs to be on bottom. And then, yeah, don't forget your next step of just writing out maybe the molecular weights of everything. So it's kind of starting with all your knowns, except in chemistry, right, we're being a little tricky because we didn't tell you what the molecular weight of hydrochloric acid or magnesium hydroxide was, but we can get that, right? And so that's the next step. Maybe you need to write it of all the elements, you know, just to kind of get you going. But I'd probably leave out what's irrelevant, but. All right, we have, oh, let's do this. Oh, let's come back to this. We'll come back. Don't want to run out of time for our reactions. So we've kind of hit a lot of them. So we did double displacement, our combinations. And so the other one we'll see a lot is what's called our single replacement or single displacement. And so one example, or let's just start the basic form, and usually it's going to be a metal or a gas or something. So a single metal in its elemental form plus some sort of other compound is going to swap and kick out that other partner like so. And let's look at an example. So one example, I can't remember if we'll do it today. We definitely might see it later. Oh, well, I can't read and write. So if we have zinc plus copper sulfate, and this is pretty cool because it starts off, and we'll put AQ, we'll put solid so we know. And this starts off as a nice blue solution, so it's a fun reaction. But you put a little piece of zinc metal in there, and zinc's going to kick out the copper, and it's going to make zinc sulfate and make copper metal. And so what's cool about this is you literally start making little pieces of copper, and it looks like rust or something since it's orange colored, but it's just little copper. So that's single replacement. And so our other type that we might see is decomposition. And probably the classic, so that's just going to be kind of one thing breaking up into two things. I should have used B plus D, sorry, B plus C. And so a classic example is calcium carbonate can decompose to give you calcium oxide plus carbon dioxide. So those are reaction types.
What's a self-reaction then? It just naturally does it over time?
Yeah.
Okay.
And so you'd have to look at the rate.
Is that where decomposition rates come in?
Yeah, I think this one probably requires more heating, but it probably does take place on a small time scale. But yeah, probably like heat would be applied. All right, so we'll get another taste for this in lab. We'll probably look at our double displacements again in lab once, again, you physically play with them and you physically see them again. So let's go back then. We'll end on this. And so let's at least summarize our theoretical. Did you have a question?
Sorry, can we go back to that page? I was writing on that.
Oh, sorry.
No, you're good.
And now we move just like a little faster during the summer. Trying to cram everything in there. I'm sorry. You guys are doing well, though. I was pleased with your exam grades, especially with the summer pace. You gotta give yourself some credit for that. You haven't had a lot of in-class practice, as you might during the year. All right, are we ready? So the last thing, and so this is also really important in chemistry and what you do on a daily basis, and also like what you're trying to go for. So like an organic chemist, for instance, right, they would want to get probably a 90% yield would be awesome, is kind of what they aim for. And you have to think about an organic chemist is sometimes doing, 20-step synthesis, something crazy. And so that's going to be, 20 to the power of 0.9 gives you your overall yield. Well, that's kind of an aside. So what we really want to calculate is, well, what's our yield? And so when you see these terms, so don't get confused. So your theoretical yield, this is always what we're calculating. So, right, this is, I'll just put like what we usually calculate. Right, so in the problem, like this one, we asked, how much CO2 we're going to make, so that's what we're asking. But then our actual yield, right, is what you're actually holding in your hand. So you as a chemist, right, you calculate your theoretical yield. Okay, I'm expecting, 1 gram of product or whatever. But then, of course, right, after you spilled half of it everywhere, you left it on your flask or whatever you did, what actually do you have purified in your hand? That's what really matters as a chemist. And so, right, that's actual over theoretical. And so we calculate that. And, just let's say we calculated, and this is obviously really easy numbers, so calculated 1 gram, but we're only holding, right, so holding in our hand 0.6 or whatever. And we calculate our yield. So then, right, we can say we had a 60% yield, which isn't too good if this was an organic reaction. If this was a metal reaction, that would probably be on par. Those tend to be like 50% yields. Or your yield can also tell you other things. So let's say you have like over 100% yield. That doesn't mean you did a spectacular job. It just means it's probably wet, would be my first suspicion, or impure. Yeah.
Is the theoretical yield just like a benchmark guess, or do you actually have to do calculations to get it?
Yeah, so that's what we get with stoichiometry, right? So that's like when the question asks, like, what do we expect? Like, how many spores are we going to get? That's what you're calculating. Yeah, so all the s'mores, right? So that's how the question would work. So we went back to like our limiting reagent question, right? We did our 300 grams. Okay, we said that our graham crackers would give us 2.73 s'mores, but let's say, right, you smashed half the s'mores in the kitchen and you only ended up with 1 s'more, right? So then this is your theoretical yield, and then your 1 s'more is your actual, so 1 over 2.73 gives you your percent yield. And we could also finish this up in lab too, since I think we have 2 minutes of official time. So ammonia can be synthesized with this reaction, so 2 equivalents of NO plus 5 equivalents of hydrogen gas give us 2 equivalents of ammonia. And so now this is a tricky one. So starting with 86.3 grams of NO and 25.6 grams of H2, find the theoretical yield of ammonia. And so this is a limiting reagent problem as well, but it did not tell you that. Let's see, so do we want to start going over them? So again, cram them in. So does anyone have the molecular weight of NO?
30.
So about 30 grams per mole. And so what is that? Oh, hydrogen. So what's hydrogen? So 2 approximately, or 2.02. And ammonia, what's ammonia?
Was 17.
All right, so then we just have to do our process again. So I'll start with NO, so 86.3 grams. So divided by my molecular weight. You mean the,
For two, right?
yeah, so we don't have to do anything. I'll write it just to be explicit. And then I might stop here in interest of laziness. And then once I find my theoretical or my limiting reagent, then I'll save the grams for the end. You could also take it all the way. So divided by 30. And yeah, this is right, this is irrelevant though. I just wrote it here so we see they cancel. And so I get 2.88, oops. So this would be, right, moles of ammonia, because I didn't finish. Didn't do the full problem. I just want to compare, so let's do the same for hydrogen. So just repeat that same process. So divided by 2. And so now they have a different mole ratio though. So 2/5. So, don't let any of the numbers confuse you, scare you, doesn't matter. 1 mole over 2.02, and then this is 2/5. So do we get 5 moles then? Ammonia? Questions?
So for the last part of, the first equation, right under 2NH3, what is that number? Is that
2NO.
2.0?
No, 2NO, like
Oh,
2.
okay.
So this is just a ratio, but really we didn't need to put it there. I just put it there. Because that cancels anyways. Yep, so limiting reagent NO, and now I can times it by 17 to actually find the gram. What'd you say? So either 48.9 or...
Wait, what do you do with the limiting reagent? Where do you go for that?
then you just multiply it by the grams, or you could have done this to begin with to find your limiting reagent.
Where's the 17?
Uh,
Weight of the ammonia.
yeah, 17 is weight of ammonia.
So I have a question. If we were to do it all together, you should get a slightly different answer than if you do it round down to your sig fig and then go through. So would that be a big deal when you're doing the full calculations, or would that be like just the room for error margin?
Yeah.
Okay, because like you got like 40, it would have come out rounded to 49.0, but I got like 48.9 when I did the full calculation.
Yeah,
Okay.
it's either one.
That would be close enough.
Yeah.
That was like, okay.
Yeah, because there's always room for rounding because your masses can be rounded, so there's error there. All right, I think we're over time now. So we'll keep practicing, and so we'll take our 10 minutes and then I'll see you in lab. And so it looks like everybody wore appropriate clothing. Yeah, hair back, all that good stuff. There'll be more burning